So we've got prime numbers we're playing with. So the question number 4 I was concerned about. So if the grid went up to 3, so we stopped at 100, but what if it went up to 300? Would I need to test numbers bigger than 7 to kind of figure out what's going on there? And so the answer is yeah, I would. So the question is, how far do I have to go? So if you think about squares and square roots are relevant to when you should stop looking. The square root of 100 is 10. The closest prime to 10 from below would be 7, and then 11. But what was the first number 7 got to knock out of the grid?
40.
It was 49. So the first number 11 gets to knock out is 121. So we only needed to check up to 7. So for 300, if we have 300 numbers in the grid and we want to check that, we'd need to know, well, what is the square root of 300? Anybody calculate that yet?
17.3 something.
Okay. So that means we need to check up through 17. If we want to find all the prime numbers that are less than 300, then 17 would get us there. So just for fun, what is 17 squared?
289.
289. So the first number 17 gets to knock out of the grid is 289, because no other number gets to knock that out yet. Because its prime factorization is 17 times 17. So no other number got to color it. Well, what's the next number 17 is going to get to knock out? Well, if you think about that, the next multiple of 17 after 289 is 289 plus 17. And what's that going to give us? 6, carry the 1, 0. It's going to give us 306. Cool thing is 17 knocks 289 out of the grid. All the other primes took care of everything under 289. The next number to be concerned about is 306, but 2 and 3 killed that one because it is even, and 3 plus 6 is 9. So question, what does that mean about the numbers from 289 up to 300? What do I know about them? One of two things.
They're either prime or will be taken out by.
Yeah, they're either prime or they were taken out by another number. Oh, cool. All right, so we got a slightly different question for number 5. Where'd it go? There it is. What is the largest prime less than 1,000? We're going to figure that one out. So I'm trying to get up to 1,000. So first number less than 1,000 would be 999. Is 999 prime?
No.
No, 9 plus 9 plus 9 is 27. 9 goes into 20, 9 goes into 27, 3 goes into 27. So that's out. What about 998?
It's divisible by 2.
It's even, divisible by 2, right? 997. That was your answer? Okay, so here, how do we know it's prime?
Its square root is just over 31. Yeah, just over.
Okay, so square root of 997 or square root of 1,000 is about 31. So that means we would have to check all the primes up to 31 to be sure. Okay, and so everyone, you did that?
Actually, I didn't.
Okay, so we don't know if it's prime or not. We got to check it out. So we'd have to go through. Well, we clearly can tell it's not divisible by 2. Does 3 go into it? Well, 9 and 9 is 18, and 7 is what, 25? So 3 doesn't go into it. 5 we can see doesn't go into it. Does 7 go into it? No. 7 doesn't go into 99, so it's not going to go into 990. It does go into 7, so there'll be a remainder from this part here, right? So we can rule out 7. We don't have to check 8 because 2 didn't work. Do we have to check 9? No, because 3 didn't work. So really all we need to do is check primes. So 11 would be next, and we have to check, does 11 go into it? We're going to find it has a remainder of 7 because of the 99. 13. There's no quick way to check 13, but division doesn't work. Okay. 14, 15, 16, 17. We have to check with division, not 17. 19. Nope. 21, 22, 23. Nope. 24, 25, 26, 27, 28, 29. Nope.
Oh, wait. Hang on, I think I'm wrong.
Oh.
No, it doesn't work.
You think it doesn't work? Okay, and finally 31.
No.
Okay, so now we're sure it's prime. So the only, and I mentioned this, determining if a number's prime is hard because factoring is hard because it involves division. Determining if a number's prime involves lots of divisions with numbers. And so we did just confirm it's prime because its square root's around 31. So we have to check all of the primes up to 31. And now we have a winner. We have the largest prime under 1,000. And it turns out there's a constant search worldwide to see who can find the biggest prime number. And every few years, somebody claims they have a winner. So I'm kind of curious, what is the biggest prime number we know right now? Largest prime number. Because every year it changes. Okay, ooh, a new one was found August of 2017 by the GIMPs. Okay, I used to be a proud member of the GIMPs. It's the Great Internet Mersenne Prime Search. It's a bunch of people that kind of connect all their computers through the internet to try and solve these problems. And it takes a lot of computing power to try and find a prime number. Wikipedia wants money. Not today, dear. But I do donate to them sometimes. Okay, so the largest known prime number is 2 to the power 74,207,000, then minus 1. It has over 22 million digits.
What are they even like?
That's a lot of.
Just see them type it out.
Yeah, how do you type it out, right? Yeah, you need a computer to type that out. Yeah, it's a really fascinating problem trying to find these big prime numbers. And I mentioned before that if you take 2 huge prime numbers and multiply them together, the time it takes, like the fastest computer on earth to factor that is like our lifetime. It's such a hard problem. And it's like, just multiplying 2 numbers together, yeah, but they're big numbers. And although multiplying them doesn't take very long, factoring them does. If you don't know what the 2 primes were that made the bigger number, it's just wicked hard computationally. The only thing that'll make it easier if we ever develop quantum computing, which is in the realm of possibility still, but I don't think it's going to be in my lifetime, but maybe. So anyway, that's a big, yeah, 22 million digits.
I don't even know like what that number is. Like there's.
Yeah, so what happens is they've got these computers that are chugging along with these programs, trying to test out numbers to see if they're prime. And a computer or a group computer like says, "Oh, we found one." So then it goes out to a whole bunch of other computers, and all those other computers have to try and confirm that this number that has 22,338,618 digits, that it really is a prime number. And it's possible. People have to write, there's special programs that, filter through these numbers, but it takes multiple computer checks to try and confirm if it's right. So for example, think about the number pi. How many decimals does pi have?
Infinite.
Well, it's infinitely many, yeah. So then the other question is, well, how many decimals have we calculated as human beings? And it turns out we've calculated a lot. Decimals of pi, it's on the order of that number there. How many do we know? Okay, so we know a lot more than the size of that number. As of 2011, we had calculated up to 10 trillion digits of pi. So that's a lot of digits. If I remember back in 2011 when we did that, I tried to figure out how, like, suppose you type them all in a book like this with size like 10 font. Okay. The amount of paper and books that you would make would easily fill this entire building, packed with books, if you tried to type every one of those digits of pi. I mean, it's just, I mean, we talk about trillion like death, but it's a hard number to wrap your mind around when you actually say, okay, well, let's list all those digits. What's it look like? You know, it would wrap around the world several times. If it were dollar bills and we stacked them, they would head up to the moon. I mean, just big, crazy numbers. But we have the computing power to do that. But I mean, out of an infinite number, 10 trillion ain't that much. It's a lot, but you know. So it's really hard. It's weird to wrap your mind around those numbers. So kind of like that when we were playing with the rice problem, you know, similar idea. What does it really mean to be that big? What's that? You didn't like that worksheet? Yeah, that was a tough one. An easier thing you can kind of do with that, a lot of schools celebrate the 100th day of school. And so they'll do things with 100. Like I remember in my daughter's class, they lined up 100 kids foot to head on the ground to see how far they would go. You know, just play around with numbers. Okay, so I think we kicked that in the butt. What else? This page wasn't too bad. Ooh, the last question. Several numbers on the grid are divisible by 3 different primes. So for example, remember when we were playing that board game where we were throwing down paper clips? 2 times 3 times 5 is 30. So it's the first number it's the first whole number that has 3 different divisors, 2, 3, and 5. Okay. What's the smallest number that has 4 different divisors? 110. 110? 210? Okay. How do we find that number?
2 times 3 times 5 times 7.
Nice. Where's my magic pen? 2 times 3 times 5 times 7. Yeah. 2 times 3 times 5 times 7 is 210. And so that is definitely the smallest number with, oops, not 3, 4 different divisors. Okay, so those are the questions that I had concerns about on this because I thought they were the harder ones. Are there any questions people got stuck on as they were working on it that you want to talk about? Tiffany?
Number 2 on the bottom of that one, right?
Yeah, the one, I guess it was right above the 210.
This one right here?
Yeah.
What was the longest string?
Was it asking like what numbers were they or how long is?
Either way you could go. You could say which numbers they were or how long was the longest string. You can interpret it either way.
Okay.
Yeah. So let me bring up my picture of that. See if we all agree on that one. Let's see. Colored sieve. Okay, so here's mine. So it seems we get bigger runs as we get up to the higher numbers. And was it between 89 and 97? That's my recollection.
Yeah.
1, 2, 3, 4, 5, 6, 7. So there was a run of 7 composite numbers was the biggest run.
Okay, thank you.
Yeah. Good question. All right, other questions?
You say between 89 and 97? Or no?
You could say between 89 and 97, yeah.
Okay.
Mhm.
Thank you.
That works.
don't do activity 5?
Correct. We're only doing 2, 3, and 4.
In chapter 5, I don't know why I haven't got this in yet.
Yeah.
We do all of them? Or is
Let me go back to our course. I don't think it was all of them.
Oh, yeah, we weren't sure about activities.
Yeah, activity 7.
5, it was 1, 2, 3, 4, 5, and 6. Activities 1 through 6
Oh, okay.
for chapter 5.
Okay, thank you.
Yep. Did you have questions about one of them, or you just wanted to know which ones?
I'm just not, I don't remember.
Not at this time. Okay, so you can ask me later, or on Monday we'll do an optional review. Anybody that wants to come from 3 to 4. Okay. All right. So let's see. I had a couple of homework questions we'll take a look at, and then. So remember, in chapter 4, we're only doing section 4.1 and 4.2. You don't need to do 4.3. We'll pick that up next term. All right, so let me find my homework questions.
I mean, on the online.
On the online homework, yeah.
Oh.
Where did I put those? I got some emails. Okay, there's one, there's the other. All right, so first one was about an idea called casting out nines. 9 has a lot of wild properties in our number system. Mostly the properties of 9 are because it's right before 10 is the biggest thing about it. If we were in a different number system, it wouldn't be as special. So what the property is, you can use it to check sums. And I don't know if anyone's ever noticed this. A lot of times when you download files from the internet, some files come with what are called checksums to make sure the file wasn't corrupted when it was downloaded. And this is a similar idea to file download checksums if a computer wanted to make sure a file wasn't corrupted during download. So the numbers 672, 301, 500 are added up, they come up to 1473. If you think of the remainders of each of those numbers, 672, 301, and 500, when you divide by 9, you get remainders of 6, 4, and 5. Now, if you add up the remainders, you get 15. And if you take 9 into 15, the remainder is 6. Turns out that's the same remainder 9 has with the sum. Okay. So casting out nines is a way to check a sum. So we're going to try that together on this group of numbers. So put that in my sheet here. Pencils are missing. Come here, digital pencils. All right. So first thing we want to do is just add these up. So 752 and 743. And so I get 6 and 9, 11 and 18, I think. And so then we want to check with remainders. So 9 goes into 321. Let's see, 9 goes into 32 3 times 27, 51, 5 times with a remainder of 6. And then 9 goes into 752. 75, it goes in 7 times, right? No, 8 times, 8 times. Switch color. 72, so remainder 3. 9 goes into 32 3 times. 27, remainder 5. All right. Find out in a minute. 9 goes into 743. 74 8 times. 8 times 9 is 72, remainder 2. 23, that's twice. It was 18, remainder 5. So if I add up those remainders, I get 16. And 9 goes into 16 once with a remainder of 7. So if I have the right sum, it should have a remainder of 7 also. So 9 goes into 18, 16. 9 goes into 18 twice. 9 goes into 1 0 times. 9 goes into 16 once with a remainder of 7. So it's likely we have the right sum because the final remainder matches for each one. So that is called casting out 9s. A weird procedure. All right, there's another homework question in 4.2. All right, so here, Mr. Arborita, oh, that's cute, wants to plant fruit trees. In a rectangular array, for each of the following number of trees, find all possible number of rows if each row is to have the same number of trees. So, possible number of rows for 100 trees. Let's see, we're just going to do that for a bunch of different numbers. Okay. So this is a lot like the rectangular grids we were looking at before. So for rectangular grids, we want to have 100 trees in the array. An array has to have a length and a width, so all we need to do is look at possible pairs of numbers that multiply together to be 100. So that could be 1 times 100, or 2 times 50. 3 doesn't work. 4 times 25. 5 times 20. 6 doesn't work since 3 doesn't. 7 doesn't work. 8 doesn't work. 9 doesn't work. 10 times 10. And so I have a repeat, so I'm done looking. So as far as rows go, any of these numbers could be a row on either side of the multiplication, because it could be long one way or it could be long the other way. So the set of rows would be the list of factors. 1, 2, 4, 5, 10, 20, 25, 50, oops, or 100. Let's see, did they try that? Oh, they just missed the 5 in there. a 5 in there, 10, 20, 25, 50, 100. That should do it. Job. So what do you think it would be for 12 trees? 1, 2, yeah, 4,
6.
yeah, 12. Not bad. All right, 17? Yeah, 1 and 17, it's prime, that's nice. 144 has a lot of factors, so I think I'll leave that for your homework. You guys can finish that one. And I think those were the 2 questions I was asked. That one. Yep. Those are the 2 I got emails about. All right. Does anybody else have homework questions? Not at the moment. Okay. What should we do next? Take a look at the practice exam?
Yeah.
Okay, let's do it.
Do you have the password for the homework?
Get it done, please. Does that sound right?
Yeah, that's the one.
Yeah. Get it done, please. Here's the homework password. Or is it get it done now, please?
I think it's just get it done, please.
I think it's just get it done, please. Yeah.
I know it started with get it done. So.
Maybe next week will be, maybe next week will be get it done now, please. All right, so remember, under resources, I posted a sample final and some answers to it. Also is a previous chapter 3 and 4 and a chapter 1 and 2. So here is this one here. So we have patterns of numbers. There'll be a problem like that on the in-class test. Could be a figurative pattern like this one here. And there'll definitely be some sequences of numbers that we have to try and continue and maybe find a formula for. Sum of counting numbers was something we played with before.
This is the sample in class.
This is the sample in-class final, yes. And you already have the actual take-home final. And I can't go over those exact questions if you have questions on something there, but I can go over something similar. So if you're stuck on something on the take-home exam, then you could find a similar question on the in-class test, or we could try and make up a similar question.
I was having a problem with number 2 on the take-home.
Number 2.
Because I don't understand what it's asking about the pattern.
With the arrows?
Yeah.
So each of those, let me bring that up.
Is this stuff, was it in number 2, like the first or second chapter?
This number 2 would be something that you saw in section 1.1 or 1.2 in the book. So for example, let me bring that up. Well, I guess it's kind of similar to this problem here, but we have dots instead of arrows. So I have 1 dot there, 3 dots here, 6 dots there, 10 dots there. So for the problem number 2 on the take home, count how many arrows there are in each figure, and then you want to try and come up with a way to continue that pattern and describe it in a couple of ways. And draw the next figure.
Can I get another one of the take-home finals? Because I have no idea what I'm doing.
You lost yours? You have mine.
Oh, wait.
You found it? So just to be clear on here, there are 10 questions you have to answer. Question 1 gives you a bunch of choices, A through E. So and it's A through E you get to pick one of. Otherwise, you need to do the others 2 through 10. And I wouldn't recommend doing A, B, C, D, and E for number 1. That'll take an awful lot of time. I mean, if you have that much time to kill and you want to do that Netflixing, go for it. Yes.
That's your question.
Yeah.
So how would you find n figure?
Yeah, I need help on that.
I've never like really fully understood that.
Yeah, so we'll do that for this one right here. And then we'll do another, I'll find another one we can do. So, whenever we have a figurative pattern, it's a good idea to count the things in the figure. So here, I've got 1 dot and 3 dots and 6 dots and 10 dots. And so I want to continue that. So I'll just draw the next one. The last one had 4 in the bottom, so the next one will have 5 in the bottom. And then 4 above that. And then 3 above that. 2 above that, and 1 above that. So that's another 5, so there'll be 15 in that figure there. And then I might make the observation here that I added 2 to the bottom to get that next triangle there, and then I added 3 to the bottom row there. I added the bottom row with 4 to get that one. I added the bottom row with 5 to get that one right there. At this point right here, I want to try and make a connection between the numbers I have and their position in a list. So I'll just draw it out a slightly different way. We have n, our counting. We have a first figure, a second figure, a third figure, a fourth figure, and a fifth figure. And then we have the number of dots. And that would be 1, 3, 6, 10, and 15. So one thing I might note is to get the 5th figure, I had to add 5. To get the 4th figure, I had to add a 4 to what I previously had. So I could just write a statement that says something like that. To get the current number of dots, and so it's just a matter of figuring out how to word it. Take the previous number and add the current position. Which you could call n, because n is whatever position we're at.
So you're wanting us to.
You could come up with a formula. So I'll come up with a formula for this next. So this type of formula right here, where I need to know the previous term, that's called a recursive formula. So if I want the 100th term, I need to know the 99th. But then I need to know the 98th and so on down the line. So I have to consecutively build up to get recursive. But it works, you know, a spreadsheet does it really easily. We can always do it one step at a time. That works fine. And our minds are really good at picking up recursive patterns. Okay, we're good at that. The other kind of formula is where I call it like the immediate gratification formula. Sometimes I call it the closed formula. Some people call it an explicit formula. So that if you wanted the 100th term, you just plugged into this formula and out popped the answer, instead of having to backtrack through the previous terms. So to figure out that, well, then I have to have some prior knowledge to kind of figure it out. And the thing I have at my advantage here is starting with 1, I add 2, then 3, then 4, then 5 to get to the 5th term. To get to the 6th term, I would just throw a 6 onto that. So then the formula for the nth term, or even let's use the, oops, that's marker, it's a highlighter. If I wanted to get, say, the 10th term, I would just add the numbers 1, 2, 3, 4, 5, 6, 7, 8, running out of room. 9, and 10. Does anybody remember a shortcut for adding up consecutive numbers?
Isn't there a number on the calculator or like a button?
That would be if they were times each other. So
Oh.
10 times 9 times 8, yeah, that's an exclamation point called factorial.
Okay.
Yeah, but there isn't a button for adding them up. But we did come up with a formula a while ago. It was a long while ago. It was related to finding an average. Does that ring a bell? What's that? The mean? It's related to finding the mean. Yeah, we twisted the formula for finding the mean or average to help us find a sum. And the trick was the numbers had to be spaced the same apart.
Is it the Fibonacci?
No, it wasn't the Fibonacci. That's a recursive formula.
Um,
So the trick was, if you take the first term plus the last term and divide by 2, that gives you the average value of the sum. If you then multiply that by the number of the count, the number of things you're adding, that should give you the sum. Okay. So my claim is that the sum is equal to the average times the count. And that's because average is sum divided by count. I'm just twisting the formula for average. So because the numbers are all equally spaced, the average value of the numbers in that list is 1 plus 10, which is 11, divided by 2. So that's 5.5, is right in the middle. If I then multiply that by 10, that's got to give me the sum. We should add, those numbers should add up to 55. That was the trick we figured out a while ago.
What if they're not like one in between each?
Doesn't matter.
Oh, okay.
As long as they're equally spaced, so they could all be 2 apart, or 3 apart, or 4 apart.
Okay.
As long as you know how many of them there are, as long as you know the count. But if they're not equally spaced, who knows? The trick is it has to be an arithmetic sequence.
Okay.
Yeah, that was the trick there. Okay, so hang on, I'm not done with this one. Do you have a question on this one or a different one?
Well, it's like the same,
Okay.
yeah, but I'll ask.
Okay, so I want to keep going because right now, so far, I still only have this recursive formula for finding any particular number, but I kind of have a new way now, right? So I can generalize this by saying if I want to find the nth figure, well, that means I just have to take the numbers 1 plus 2 all the way up to n. So our trick is, because they're equally spaced, to take the first term plus the last term and cut it in half. Multiply that by how many there are. How many are there in the list? N of them, because that's what I'm at. Yeah, so that would be the formula right there. So you could leave it like that, or you could clean it up. If you cleaned it up, you could distribute this n to that sum. So it would be n squared plus n over 2 would be another version of the formula.
And then to find out how many are in the sequence, you just subtract the first or the last number from the first number? Or is that-
It depends on how they're spaced.
Okay.
We can do one of those problems in a minute too. Okay, I'll put that on my list of things to do. So here's this right here is the nth term formula. Now if somebody says, hey, what's the 100th term? I just plug 100 in and out pops the answer. With the previous one, if somebody said, find the 100th figure, I would have to figure out, well, how many are in the 99th? And then I would have to add 100 onto that. I would have to know the 99th in order to do that. All right, Caleb, what was your question?
You actually answered it.
Okay. All right, so let's see. Do I have a question like Tiffany's looking for already on here? Don't, but I can make one up. So let's see. So the question was, I think it was something like this. Suppose we had 3 and 7 and 11 all the way up to 199, I'm pretty sure is in this list. I'll do that in my head again. Yeah, I'm pretty sure. So is this what you were thinking about, Tiffany? Something like this?
Yes.
Okay. So the question is, we can easily find the average because we know the first and the last. So part of finding the sum here is going to be taking 3 plus 199 and cutting in half, because that'll find us the middle value, or the average value. The next thing we have to do is figure out what is the count of this. So that means I have to make a connection that this is the first, sorry, no color, that's the first, that's the second, that's the third. This is the nth one, but you know, which one is it? Is it the 35th? Is it the 100th? Is it something else? And there's a couple of different ways to do that. So if you just subtract the, you know, like say we were only going up to 11.
Mm-hmm.
If you just take 11 and subtract 3, what does that give you? 8?
Yeah, and that wouldn't work.
Yeah, so that wouldn't work because that's the third term. So what we have to factor into that is that what's the spacing between these numbers? So they are what, 4 apart?
Yes.
Okay, so let's do that again. Well, 11 minus 3 is 8. That's 2 4s. So that takes into account that we added 4 1, 2 times. But that's not the second term. It's the third term. So how would I tweak that? Subtraction. So what we did is we took a term, subtracted the first term. That gave us how far apart they were. We divided it by the distance between them, 4. That told me how many times we added 4 to get to that spot. So again, 11 minus 3 is 8. 8 divided by 4 is 2. I need to know that the answer is really 3. What would the next number in the list be? Be 15, right? What's 15 minus 3?
Well,
12. And what's 12 divided by 4? 3.
Just add.
Yeah, just add 1 to that, because that tells me how many term pieces I added. I need to know. I already started at term number 1. Yes, let me just add 1 to that. So you can kind of play around with a system like that to figure it out. I'll go over another way in a second. So if I take 199 and subtract 3 from it, that's going to give me 196. Dividing that by 4, 4 goes into 19, what, 4 times? There's a remainder of 3. That gives me a 49, but I have to adjust that. So it looks like that's the 50th term. So the other way to double check that, 3, 7, 11, 15, to find a formula to this is in the following way. Note what the pattern is. +4, +4, +4. Since we have repeated addition by 4, there has to be a 4 times n in the formula. If we check that, what's, for example, 11's the third term, 3 times 4 is what? 12. I want the answer to be 11. How do I fix this? Minus 1. That gives me the 11 I want. So it looks like the formula. So if I want to find out which term 199 is, I just set it equal to 4n minus 1 and solve. So that's the other way we did it before. So if I work that out, 4n minus 1 equals 199, add 1 to each side, or n equals 200, divide by 4, oops, I get n is 50. Yeah, so two different ways we figured out, yeah, it's the 50th term. And so then we can finish it off and find the sum. Good question. All right. How about, all right, we have some continue the patterns here. Let's give these a shot. So 1, 3, 4, 7, 1, 3, 5, 7, 1, 3, 6, 10, 1, 3, 9, 27. Which one do you want to do first? All of them? Write something down. Let's try 1, 3, 4, 7.
I had a question on the homework. If I find it, could you help me?
Sure.
How far do you want us to go?
With this one right here? We just want to be able to identify a pattern.
Okay.
So let's see, is that what I wrote down? 1, 3, 4, 7? Right here, right? Yeah. All right, so what could be a pattern here? Let's see. Here I jump by 2, and then I jump by 1, and then I jump by 3. That's kind of weird. What do you think, Ashley?
Yeah, the two previous terms.
Yeah. So that doesn't look like it works. 1 plus 3 is 4, 3 plus 4 is 7, 4 plus 7, so we have a prediction the next term would then be 11. 7 plus 11 would be 18. Now, as far as describing this, there's a couple of ways you could describe it if you wanted a formula. One way is to use the notation. So if I called this sequence A sub 1 is equal to 1, A with a subscript 2 is equal to 3, A sub 3 would be equal to 4. So the subscript means just what number in the list do I want. So if I wanted to write a formula for the nth term, I would just say get the term before it, that would be A sub n minus 1. Add to it the term before that, that would be A with a subscript of n minus 2. If the subscripts blow your mind some days, you could always just write that in English. Add the two previous terms. Now there's a catch here. This is a Fibonacci sequence, but it turns out there's lots of different Fibonacci sequences. I would also have to add to this which to start at. And so I'd have to say A1 equals 1 and A2 is equal to 3. So the formula is only complete if it has a place to start. You've got to have two terms to start with. So anytime you give a recursive formula, you not only have to say how to use the formula, but you also have to say where to start. Otherwise, you can just write it in words. Even in words, though, you have to still say where to start. Let's try another one. What do you think? 1, 3, 5, 7, 1, 3, 6, 10. 1, 3, 5, 7 it is. Sequence B is 1, 3, 5, 7. What's likely to be next?
9.
9, yeah. This one pretty consistently goes up by 2. And continues that way. If I wanted to put a formula, I got a couple of options. What could one of the formulas be for the nth term? Yeah, that would be one way to write it. 2 times n and n minus 1. Because we have repeated addition by 2, repeated addition is multiplication. So the formula has to have a 2n in it. And if you check that, like here's the third term right there. 2 times 3 is 6. I need it to be a 5, so I adjust by subtracting 1. All right. Taylor, did you find your problem?
I actually found it. It was like the first question answered.
I already answered it?
Yeah.
Okay. All right. Should we try another one of these or move on?
Could you do an example of like converting numerals to like base 10,
Mhm.
like base 5?
Yeah. Let's see if there are any on the sample here. Zoom out a little. All right, so here's one. 1324 base 5. So whenever I deal with any base number system, there's a couple of things I need to think about. One is that we're grouping by 5. Two, the digits I have to work with are 0, 1, 2, 3, and 4. I'm going to have 5 digits in this case. And then the third thing I want to think about is the place values. In a system like this, place values are going to be powers of the base. So if I write down a few places, we're going to have the 1s. And then the 5s, oops. And then we're going to have the 5 squareds, and the 5 cubes, and the 5 to the 4ths, and so on. So 5s, that would be 25s here. 5 times 25 is 125. If I want to do it farther, the next place would be 5 times that, or 625. So to get each place, we just keep raising the base to a power. So now if I want to talk about what this number right here means, well, the 4th place there are the 125. So that would mean in expanded form, I have 1 125, I have 3 25s, and I have 2 5s, and I have 1 1. And then we just have to clean that up. What does that give us? 125 and 75 and 10 and 1 equals, I think that's 211. Anyone else get that?
I struggled with that.
What's that?
1 1. Wouldn't it be 4 1s?
Oh, shit.
That's what I was wondering.
Yeah, there would be 4 1s. I don't know where I got the 1. I probably looked right here. 4 1s. Okay, so that would be 214. Thank you.
This is like the first time this actually was recorded.
Oh, good. It's funny how that kind of thing happens. I remember when I was taking lots of math classes, I survived a class, and then all of a sudden the next term, the teacher would say something, and I'm like, oh, that's what we did last term. I get it. The thing about math is you got to get used to delayed gratification. Light bulbs come on later. So I've experienced a lot of that. If you can't handle that, you'll never go into a math type career. People that can deal with it, yeah. Turns out I could deal with it for some reason. So let's try to go the other way. Let's take a number of base 10 and try and put it in base 5. So these are the important things in either direction in figuring that out. So how about we take 379. So that's a base 10 number. I would like it to be in base 5. And so there's a couple of ways to do it. There's the counting back change method, and then there's the repeated division method. Does anybody have a preference? I love that one too, yeah. Repeated division is a really cute way to do it. And so what you do there is, a calculator is helpful for this. You take 5 into 379, and you write down what the quotient and remainder is. So let's see, 5 goes into that, 7, 5, I think remainder 4. Somebody verify that for me.
Yeah, that's right.
Okay, so 75 remainder 4. And then I just keep repeating that. So now I take 5 into 75. So 5 goes into 7 once, and 25 5 times, remainder 0. And do it again. 5 goes into 15. 3 times, remainder 0. Interesting. 5 goes into 3, 0 times, remainder 3. And that's the key when to stop. When you have to take it that last step to say, hey, it didn't go in, but this is the remainder. And then when you read the number down this way, that's the answer. So 3004 is in base 5 what 379 is in base 10. Double check. To double check, I have to name each place value. So these are the 1s, those are the 5s, these are the 25s, and these are the 125s, right? So that means expanding that, I have 3 125s, no 25s, no 5s, and 4 1s. So 3 125s is what? 375? Plus 4 is 379, it works. Yeah, so this is definitely the answer. The alternative way to do it is to look at the place values and find the biggest place value you can use. What's the next place value after 125? Anybody remember? Yeah, 625 is too big. So then what I would do is I say, okay, how many 125s can I take out of 379? And we would find we could take 3 of them. And then I would look at what's left over and say, okay, how many 25s are in that? How many 5s are in what's left? How many 1s? So like I said, counting back change. Always give the biggest bills first and then work your way down. That's the other way to look at it. How about Mayan? Anybody remember that one? That's my favorite. So Mayan's a little bit different. Yeah, the clamshell, the sticks, and the rocks, yeah. So Mayan is base 20. But it's not a traditional base 20 because instead of having 20 digits, they only have 3 digits. So the digits in Mayan are a clamshell is a 0. A pebble or a dot is a 1, and a bar or a stick is a 5. So they only had 0, 1, and 5 for digits. As far as grouping goes, they grouped by 20, but they grouped vertically. So the first group of numbers you see in Mayans is always going to be the 1s. The next group above that will be the 20s. And then 20 20s goes on top of that, so that would be the 400s. $2,400s, what would that be? 8,000s? That would be next. I'm not sure if the Mayans went bigger than that, but I think that's far enough for us. So let's take a number of ours and turn it into Mayan. So for example, the year, 2017. We'll make that into Mayan. To do that, we have to use our repeated division trick. Let's actually shift that sucker down. And again, Mayan groups by 20, so we do repeated division by 20. So 20 goes into 2,000. It goes in one time there, and then it doesn't go into 17, so 100 remainder 17. No. Yes, is that right?
Mhm.
Yeah, that's right. And then we take 20 into that. 20 goes into 100 5 times with a remainder of 0. And we have to keep going until we get a 0 on top. 20 goes into 5 0 times with a remainder of 5. So in the Mayan number system, I'm running out of room here. Let's see, where am I going to put this? I guess I'll slide this over. It's too far. Shrink it a bit. So in Mayan, I would have 3 places. One place would have a 5, which would be a bar. There would be a clamshell under that. And then there would be 17 under that. So those would have to be tightly packed. So 1, 2, 3 for 15, 16, 17. So that would be 2017 in Mayan. 5 400s, no 20s, and 17 ones. The check, we would expand it out by taking 5 times 400 and 17 ones. Other base problems you want to look at, or is that good there? All right. So what else do we want to look at? Let's take a look at number 14 here on the take home. So illustrate and explain why the standard algorithm works for 24 minus 1. We did a couple of questions like this in class and on tests. Another one I asked that's similar to this is, why does our standard multiplication algorithm work? So when you do something like this, you want to do a couple of things. Number one, it says illustrate, so that means you're going to need to draw a picture. Explain means you got to write some words down. And we want to show the standard algorithm and compare it to our illustration, something like that. So why don't you start writing out 21 minus 4. And then think about what model you would use to illustrate that. And think about the standard algorithm. What's the key about our standard algorithm? How do you do 21 minus 4? Do I just write the answer 17, or does something happen in between?
You have to borrow.
Yeah, so the thing we're trying to do here is we're justifying, like, why the heck can I do that? That is such a bizarre thing to do when kids first start doing it. So we want to illustrate why can we borrow is the gist of this question. So to justify that, I would whip out base 10 blocks and demonstrate what borrowing means with base 10 blocks. So start drawing that out and we'll talk about it. So my story would go something like this.
So let's see that one.
Color. Do I have enough of an explanation here? I have an illustration. Do I have enough of an explanation, given what was asked in the question? I think I'm missing one little thing. Let's double check the question again. Question was, illustrate and explain why the standard algorithm works. Have I connected my illustration to the standard algorithm yet? Have I mentioned anything about the standard algorithm down here? Yeah. So what could I mention next that connects to the standard algorithm?
Borrowing is the same as trading.
Yeah, so borrowing is the same as trading, and so what we're doing is revising 21 as a 10 and 11 ones. Okay, so that's why borrowing works. Yeah, so I would just add that. All right, so I could say something like 20 and 1 is the same as 10 and 11. That just allows the subtraction to work a little easier. Yeah, so we want to, whenever we use a model, we should say, what is the, where do we get the model? And it's simple. Subtraction means takeaway, or it could be subtraction means comparison, or it means number line. You decide which model you want to use, and then do it. And then if I do say compare to an algorithm, then find a way to compare what you did here to the algorithm. So we're going to show the algorithm, state our model, explain our model a little bit. It's not just enough to draw the picture, and then make that connection between the model and the algorithm. And if you can do that, then you deserve an A in this class. That's like the big thing here, making those connections. All right, Caleb, you have something? No, just breathing?
Yep. All
right, breathing is a good thing. All right, so we got a bunch of subtraction algorithms, multiplication algorithms. Let's take a look at some positive and negative stuff since we just recently worked on that. So a good question is that 17, what's the opposite of a number? And we talked about that in a few different ways. So come up with a couple of ways right now to explain what does it mean to be the opposite of a number. here's one way I might mention it. We talked about this in class. Opposite side of 0, but the same distance away. So the opposite of -3 is 3, or you could say the opposite of 3 is -3. What were some other ways we had to talk about it? Maybe remember another way?
If you add a number to its opposite, you get 0.
Yeah, so I could say the opposite of -3 is 3 because -3 plus 3 equals 0. So those are opposites. Okay? Anybody remember a third way we talked about? There was the algebraic way.
Never multiply by -1.
Yeah, it's just a number multiplied by -1. Yeah. So the opposite of 3 is -1 times 3. Now there I have to know how to multiply by negative numbers, which complicates matters. Similarly, the opposite of, say, -5 would be -1 times -5. And I'd have to know a negative times a negative is a positive. But that's the algebraic way to think about it. So for us, elementary or middle school, these are the better options here for opposite. All right, cool. All right, how about 18? Explain why -3 plus 4 is 1. So think about a way you could explain that. It may use pictures, it may not. It's up to you. I didn't notice I didn't specifically say illustrate. I just said explain. Picture's worth 1,000 words, so you could draw pictures, but you don't have to. So come up with some way to justify to me or an elementary school kid why -3 plus 4 should be 1. So write something down. What do you think? All right, so options for this, you could use the chip or charged particle model. Another option would be to use the number line model. You could talk about money, gain and loss, or debt. Anyone do something that wasn't one of those three things? So for example, I'll show you what I wrote down in my answer key for this one. So I use the charged particle model. So I said a plus is a positive one, a minus is a negative one, and if I put a plus and a minus together, that's a 0. Other thing I need to know is what add means. Add means to combine. So if I start combining things that look like this here, then I'm going to get a 4 and a -3. When I put them together, I get a bunch of zeros, and there's only a 1 left behind. And so notice down here, I have a little explanation to go with my steps there. The number line model is a great one too. With the number line model, you would say something like a +4 means go 4 right, a -3 means go 3 left. If you start at 0, where do you end up? Right? And the kids can trace the number line and end up at 1. That would be a cute way to do it too. Questions on either of those? And these solutions here are on the website. All right, let's try. How about, we're going to do subtraction or multiplication next? Multiplication, good choice. I love multiplication. All right, so come up with an explanation of why you think 3 times -2 should be -6. A variety of ways to do it. So there's one way. Would it be okay to say it's -6 because a positive times a negative is a negative? Would that be enough, do you think? Then the question is, well, why is a positive times a negative a negative? So we have to justify that somehow. Another way to do it would be a pattern. Remember the patterns we looked at before? So to do a pattern, we start off with things that are kind of obvious, like 3 times 3 is 6, 3 times 2, oops, wrong one. 3 times 2 is 9. 3 times 2 is 6, 3 times 1 is 3, 3 times 0 is 0, and then we start getting into the place we're interested. 3 times -1 and 3 times -2. And so we would just justify here, as we jump down here, we're taking away 3 each time as we move down this list. And what's 0 minus 3? Oh. And then -3 minus 3 would be -6. So that'd be another way to go about doing this with patterns. I really like the pattern approach. But again, with the pattern, you're going to start with, so the key about patterns is starting with known facts. And sometimes for more complicated patterns, I have to show a couple of patterns before I get to the one I want. Like that worksheet we did a while back in chapter 5. All right, so we're almost out of time. So one thing I left off this practice are questions about chapter 4. So let's consider a couple of chapter 4 questions. Oops, my slides got out of order. So I think the big things in chapter 4, and we didn't finish chapter 4, we only did sections 1 and 2. Next quarter we'll do section 3 and review sections 1 and 2 again. We have the idea of primes and composites. Those are two big ones. With respect to that, we had divisibility tests. We had prime factorizations. And we had listing factors. I think those were the main ideas. So let's take a look at the last two, prime factorizations and listing factors, because they incorporate the first three main ideas here. So let's take, for example, the number 240. So the first thing I want to know about 240 is, what is the prime factorization? So I think if my factor tree is right, I found there were 4 2s, 1 3, and 1 5 in the prime factorization. Our main tool there is a factor tree. Does anyone remember the trick we went over the other day? How you can look at the exponent version of the prime factorization and you can predict the total number of factors? What the trick was? What did we do to the power? Almost not add the powers. Ultimately, we do a multiplication, but we had to do a trick before the multiplication. And the deal was 5 could either be there in one of the factors or not. So there's 2 ways to use 5. It's either present or it's not present. There's 2 ways to use 3. It's either present in a factor, like in 30 and 15 and 60, or it's not. So there's 2 ways to use the 3. How many ways are there to use 2? 5 different ways, yeah, because it could be there as a 4th power, a 3rd power, a 2nd power, a 1st power, or it could be not there at all. So it turns out you take the exponents, add 1 to each, and then multiply those together. So 2 times 2 is 4 times 5. So there should be 20 factors that 240 has. So my next question for you is, what are those 20 factors? Can you find those? So we don't make a factor tree here. What do we do here?
What'd you say? You add the exponents, add 1, and then what?
So the trick here is you add 1 to the exponent.
Yeah.
So 1 plus 4 is 5, 1 plus 1 is 2, 1 plus 1 is 2. And then you multiply those resulting numbers together.
Gotcha.
Yeah. So that was that fundamental law of counting we had with a little twist. Yeah, so there, according to this, where I'm predicting there should be 20 different factors. What are those 20 factors? We had an algorithm for figuring out what those 20 factors were. What was that algorithm? How do you describe it?
Find out what the factors are.
Mm-hmm. What's our routine for doing that?
Oh, we list them out until.
How do we list them out? It's not a factor tree, because that's a way of listing out factors, but it's not what we want. It doesn't give us all the answers. Yeah. Yeah, here we look for factor pairs. So 1 times 240, 2 times divide, see if 2 goes in, 120. Does 3 go in?
Yeah.
3 goes in, I think, 80 times. And then we check 4. And 5. 5 times what? 48. And 6. I'm running out of room. 7, nope. 8, I think 8 works. Does 9 work? 2 plus 4 is 6, nope. 10 works. How many numbers there? 11 doesn't work. Does 12 work?
Yes.
Yeah, 12 goes in, what, 20 times? 13 doesn't, 14, because 7 didn't work, 14 won't. 15?
Goes in 16 times.
15 goes in 16 times, and that's nice. 15 and 16 are right next to each other, we get to be done. Yeah, so we keep going until we find ourselves starting to repeat through the list. What if it looked like there was going to be a huge distance between this number and that number? How else could we check when to start? Stop.
Take this one.
Yeah, take the square root of that number. So just for fun, whip out your calculators. What's the square root of 240? It's going to be right between 15 and 16. It'll be 15 something. Yeah. Square root is SQRT in Google. 15.491 something. Yeah, so it's between 15 and 16, which makes sense according to our list. So if it looked like man, when is this going to end? That can help us figure out when to stop looking if there's a big distance between the last pair. And just double check, we have 2, 4, 6, 8, 10, 12, 14, 16, 18. There's our 20 different factors that were built from those prime numbers. Those prime factors. Oh, what a full day. We just reviewed 10 weeks worth of stuff. Man. All right, so this is a good time to stop. The take-home final, again, you want to finish that up by next Wednesday. Monday is an optional review from 3 to 4. I can't stay longer because I got to run to Hermiston to do an hour of code party. If anyone wants to do an hour of code party, we'll have one in Hermiston on Monday night and one here Tuesday night. There'll be snacks.
Training is still tomorrow.
There's a training tomorrow night. Yeah, if you want to come, you're welcome. We'd love to have you. I saw you signed up. That's wonderful. All right, what you got? Stuff to hand in?
Yeah.
All right, thank you.
Can I show you something?
Yeah.
What I can figure it out.
Yeah.
I cheated figuring it out.